Okay, now we're starting into the science, which I'm sure is going to excite many of you. So Stephen Quiring was unable to come, had something come up. Regrets not being here in person. I think he may be joining us online now, if not now, soon. So I'm going to just moderate this first session. We're going to be focusing on networks and getting some information updates, research results using network, Soil Moisture Institute network data to solve problems. And our first speaker is Katalin Szlavecz. Mike didn't think I could pronounce that name, but since my name is Szlavecz, it's not so hard. Anyway, she'll be speaking to us on soil moisture monitoring in the urban landscape.
Thank you very much. Good morning. My two co-authors is Ian Yassilonis from the U.S. Forest Service, who is here, and then Magda Talabur, who is, Ian is a soil scientist, and then Magda is a modeler working, he's a postdoc at Johns Hopkins University working at the microclimate urban hydrology interface. And this is not going, which way is going, which down, this one, not this one. I was pressing that. Okay, I could have the thing. Okay. Oh, there's that as well. And is it also working? Oh, it's working. So I'm going to talk about three things very briefly, starting with all the things that we heard yesterday of how difficult to measure soil moisture because of a lot of things and the kind of metadata we need to collect to properly interpret soil moisture data, how those things are even more difficult when you try to do it in an urban landscape. And then I'll talk about why we think this is still important, and I'll show you some. Okay, so we start, obvious thing is how the urban water cycle, hydrological cycle is altered. And the main difference is down there, the tremendous amount of runoff, which is associated obviously with the large percentage of impervious surfaces. So this cartoon, I think, is very simplified because there's not a single tree in this diagram, but the urban landscape is actually a lot more complex than this one. And in fact, it's a patchwork when the conditions range from different proportions of pervious and impervious surfaces, different proportions of vegetation cover. And what that results in is a patchy landscape. And so we do have a lot of my examples are coming from Baltimore because that's where I work. We have quite a bit of vegetation cover. The darker greens are forest and the lighter obviously lawns, people's residential lawns, parks and so forth. But we do have vegetation cover, which means we do have exposed soil surface which have soil moisture. And even a very densely populated residential area, such as this one in West Baltimore, has green things in it. So it has exposed soil. So the other major difference, of course, is how the urban soils are altered. And, you know, impervious surfaces, soil sealing is just one of the major changes that's happening in an urban area, but there are other things related to physical disturbance, soil transports, and so on, some of which are listed in here. And what that results in, of course, is this enormous diversity of soil profile, most of which is not a naturally developing soil profile, which is extremely difficult and challenging to describe, to categorize, and to understand their functions. And that's happening in the third dimension, but on the top of this complexity, there is also management. So yesterday we talked about soil organic matter might be an important metadata item. So I'm just illustrating here how difficult even that is to describe in an urban setting. This is Cobb Hill in North Baltimore, and I will show some other data later about Cobb Hill, a typical residential area where you have individual single homes and the property, and this is a very fine scale assessment of soil organic matter on the surface. And as you can see, the ranges are enormous. And compared to the forest, which is fairly uniform, we have all kinds of values here. So this is what we have to deal with. But we think this is important, nonetheless, to understand urban soil properties, including soil moisture conditions. One of them is urban agriculture, which is very different in scale, obviously, than what most of you are familiar or thinking about, but nonetheless very important. And it is important because many of cities like Baltimore has a lot of vacant properties, vacant lots, which can be turned into beneficial green spaces. And also because many of these places are in this, what we call healthy food priority areas. These are the shaded areas, which is a nice way of saying food deserts. These are places where people do not have access to fresh, healthy produce. So very often they grow their own. This is an increasingly popular activity in cities. Now, these urban farms or gardens can be a lot more easily manipulated or managed to whatever we desire it to be. And so that relates to, for instance, water holding capacity. And so these soil moisture measurements is showing is that when you create a high water holding capacity plot, that reduces the need for irrigation. This example is from California, where obviously this is a big issue. So one of the main issues, again, going back to the runoff issue, is stormwater management. So we no longer look at cities and want to manage runoff just to get rid of it and get it to the storm sewer system. We want to create multifunctional spaces which do this ecosystem service at least partially for us, such as rain gardens and just green spaces and so on. And so to measure or to assess how well they perform, we need soil moisture measurements. Additionally, the soil moisture measurements can improve hydrological models because, as I'm highlighting here, many of those models make unrealistic assumptions about runoff, which is not supported by observational data. So yesterday we also heard about how soil moisture is related to energy balance. The kind of surfaces we have, the kind of land cover we have, relates very strongly or determines land surface temperature, and which is then very closely relates to people's sense of heat or their own well-being, okay? And so if we do not have soil moisture data, observational data, people try to model it. And because the models are often very coarse scale models, such as the one on the left-hand side. This is Baltimore again. And so this is model data using WRF, a very coarse scale 30-kilometer atmospheric model. And so as you can see, it doesn't pick up anything about this heterogeneity as I talked about. Whoa. So anyway, the right-hand side is what Magda's PhD work was, to combine this atmospheric model with a hydrological model called PARFLOW, which then started to pick up more complexity of the landscape. You see streams and then green spaces and so on. And so this is good because it also improves the land surface temperature predictions. This is Landsat data, so observational data. This is the combined data, which is much closer to the observational data than that without it. Okay, so a few examples of how soil moisture varies. This is actually infiltration rate related to bulk density, very small scale, 40-meter scale in a grassy area. This one is showing the importance of O-layer. I mentioned we have forest patches. Often they are very thick. We have a duff layer. Often we don't have anything. This is typical for our forest, and it's related to earthworm invasions. Earthworms are devouring the O layer and mixing it into the A horizon. I'm gonna skip this. So we also talked about land cover variations. Here again, we have the Cobb Hill that I mentioned. We, many years ago, had a wireless sensor network operating here for over a year. So these are the individual networks. And what I'm showing here is 3 months of data, the two major land cover types of forest and grass. And then these are the individual sensors, which are highlighted here, just a subset of them, how they react to rain events. And then just to show the colors, the differences between the grass cover and the forest cover, but also within land use type variation, how these different locations can also be different. Okay. And so that becomes important, of course, even more important in extreme events such as Hurricane Irene, where the grass reacted much more strongly, this large amount of rainfall that received in a 24-hour period. So in summary, I think the urban measurements of urban soil moisture, or including urban landscape, is important because it, first of all, improves both hydrological and microclimate models and the combination of the two. Both of these things can or do have management or even policy implications because they are directly related to how we manage stormwater and people's well-being. And then while we understand that the urban land cover is very small in proportion to all the agriculture and forested lands that most of you are familiar with, the number of people who are actually affected by those conditions are disproportionately larger. And many of those residents live in underserved, low-income communities with very little power of doing something about extreme conditions, such as heat wave, for instance, that we hear a lot about. And for these reasons and for others, we think it would be a good idea to include the urban landscape, at least some cities, into this national soil moisture monitoring network. Thank you.
Okay.
Should be.
Any questions? Okay.
Those urban soils are really interesting because they're so dramatically disturbed and manipulated. Do you foresee the ability for those soils to heal themselves, to rebound after you convert them back to farmland, say on an abandoned lot? Or do you have to bring in amendments and do extra work?
You have to bring, you have to bring in amendments. So abandoned lots are actually created following certain protocols, and it's changed over the time. So in the past, what they were doing, I mean, abandoned lots essentially had these abandoned buildings, which are typically row homes in Baltimore and many other places. And what they used to use is essentially during demolition, they put all the rubble, or as much as they can, into the basement to fill that void in, and they put a thin topsoil layer. This is no longer, but these are old abandoned lots. This is no longer allowed for a number of reasons. So now they actually had to excavate and fill in the basement with a certain pre-described layers of soils and gravel and things like that. So those are higher quality soil in terms of, you know, more resembled of what, you know, you can have soil layers, but there's always amendment. And in order to agriculture, you definitely need to amend the soil with organic matter and other things.
One more. Okay.
I was wondering all the differences in moisture that you showed between forests and grasslands. They were very interesting. Could we relate them to LAI? Like, was it because of different rates of interception that the moisture didn't reach the soil, or do you think it's more a function of soil properties that you were seeing those differences?
I think it's probably both. Obviously, there's a lot of through flow in a forested area. So, but we think that this network was fine scale enough, maybe to capture that, even what's coming down, you know, nearby a tree, because these were 10 meters apart, roughly. The other one is clearly soil texture differences. So the grassy area is much more man-made. The forest patches are still retain their more or less natural horizons. The grassy area is usually not depending on what the site history was, what was there before.
Great. Okay. Thank you very much, Katalin.